Hello everyone. Today we are presenting a biomedical instrumentation designed for soccer players. We came up with this project from an incident during the European Football Championships in 2020, when Christian Eriksen suddenly collapsed and endured a heart attack in a game, and it shocked the world and sports fans. Although the cardiac arrest does not happen frequently, it raises the concern for athletes because of its high fatality risk. So, what we are proposing is a device to track the vitals and performance metrics so that the soccer players can ensure their safety as well as improving their skills in the game. To build this project, basically we solved three problems at hand. The first thing is collecting the biomarkers on players and develop a quantitative method to analyze them. Then we packaged the sensors and processors to make a usable prototype. We also create an application for connecting our device to a computer, then visualize the data we collected.
Our design features a PPG sensor that uses a photodiode and LED to measure heart rate, which could then be used to detect irregularities and exercise intensity. And then we have a GSR sensor, which is used to measure skin conductivity with two electrodes to determine hydration or muscle cramps. And we also use an IMU, which houses an accelerometer and gyroscope to measure performance metrics of the athlete. And lastly, we use a thermistor for measuring temperature and whether there is a risk of heat exhaustion. All of these sensors are connected to the embed, which is housed in a 3D printed enclosure, and all of that is secured to the leg with a nylon band. Looking into the specifics of GSR, it's used to measure the electrodermal activity of the skin, where sweat and other psychological factors can directly alter the electrical characteristics. And two components of GSR are measured with our configuration being both tonic and phasic. Tonic is the slower time-varying skin conduction that varies from tens of seconds to possibly several minutes, and that is typically called the skin conduction level. The baseline of this is dependent on the individual and is generally related to autonomic reasons. The phasic component is a highly rapid event-based fluctuation, which basically represents the instantaneous change in skin conductance. And finally, for measuring temperature, an NTC thermistor is used, where the temperature and corresponding resistance have an inverse relationship. And we utilized the Steinhardt-Hart method, which allows us to basically derive temperature from the measured resistance. And as shown on the graph, you can see that the temperature increases and decreases rapidly depending on contact with the skin.
For heart rate, we use a simple PPG sensor. Compared to ECG, PPG only requires sensor in one place on the body. I firstly designed and simulated the circuit on LT Spice, and so my design has a transistance amplifier that can convert the current from photodiode to voltage, and a Bessel fourth order bandpass with cutoff frequency at 0.6 Hz and 4 Hz, and 22 times gain. After the simulation proves my design concept, I built a breadboard circuit based on the schematic. After testing the circuit, I designed a PCB board that contains LED and photodiode, skin temperature sensor, and IMU. To determine the heartbeat from PPG, I simply set threshold, and when the measurement reaches the threshold, it counts as one heartbeat.
So here is our accelerometer and gyroscope, and we count our steps information from IMU outputs. As the figure is shown on the left, we found out that one axis will have relatively large periodic acceleration changes, no matter how the player wears the pedometer. Hence, peak detection and a dynamic threshold decision algorithm for acceleration on all three axes are essential for detecting a unit walking or running circle. So our step count algorithm consists of four main parts. First, we adopt the mean value of sliding window spatial filter to smooth the result. Then we use the dynamic threshold to detect the step. The algorithm updates the max and min value on 3 axes dynamically to find out which axis is the current active axis. But we found out that sometimes the algorithm seems to be too sensitive, so we further employed the precision control mechanism to filter the abnormal points and cancel the high-frequency noise. In the end, we have our step detection part. We analyze the samples on the most active axis every 200 milliseconds. A step is defined as happening if a elective slope of the acceleration plot when the acceleration curve crosses below the dynamic threshold.
There were many considerations taken into account when going about the packaging and design of our breadboard prototype. The most important was skin contact with the sensors. We created a housing component that had cutouts for the sensors, the large rectangular cutout for the thermistor, the circular one for the PPG, and the small cutout for wiring to connect the GSR unit to electrodes that are sewed onto this nylon band. We also wanted to ensure sufficient pressure to try and avoid motion artifacts as much as possible and to get clear signals, which is why the nylon band and knee sleeve are used. Rigid housing also ensures that there's not too much movement of the components with the shifting and stretching of the skin. The nylon band and knee sleeve also met a lot of our customer needs, including being size-friendly, comfortable, and staying in place during exercise.
This is our second version prototype. I designed a PCB board contains all the sensors except GSR. You can see that the PPG sensor, skin temperature sensors are on the front of the PCB, and the IMU was soldered on the back of the PCB. The PCB board is printed at ME Electronics Lab. The PCB is extremely small compared to the mechanical packaging. It's only 3 centimeters times 3 centimeters, and it's also wearable after we cut off all the exposed pins. But the disadvantages of this version PCB is that it uses jump wires to connect it to embed. Our device can be battery powered, and to make it fully wearable, I bought a HC06 Bluetooth module and used serial port to transmit the data from embed to PC. I developed a C# Windows application in Visual Studio for real-time data visualization, as shown here. I made 4 plots for each sensors, and you can see the detailed data of each transmission is shown in the middle of the application window. The transmission rate of the Bluetooth is 200 milliseconds, which means it transmits 5 data in 1 second for each sensor.
In the future, we would like to develop more accurate heart rate sensors. Currently, our PPG circuit is effective, but the LEDs sometimes give us a hard time, and commercial PPGs that we experimented with had a lot of noise. We would also like to add more performance-based sensing, like determining how long a player sprinted versus walked for, or the number of shots on goal. The team will ideally create a smaller dimension design with the possibility of flexible housing and a flexible PCB. Additionally, the use of a microcontroller rather than Mbed or Arduino would be more ideal. For the connectivity of the device, ensuring the app with real-time visualization is fully functional and provides a stable Bluetooth connection 100% of the time is crucial. Overall, the device allows for soccer players to improve their skills while also keeping track of their vitals. It's exciting to think about the future development possibilities of a device like this and how its sensing capabilities can be used in other aspects.